Okay, thank you everyone for joining. So today we have a colleague from Liège, Valentin Christiaens, and he did his master degree in University of Liège, and then he stayed there to do his PhD. It was a dual PhD between the University of Chile, if I understand, and Liège, so he divided his time between Belgium and Chile. And after that, so he obtained that PhD in 2018, and then he moved on to do a postdoc in Australia, in Monash University. And he stayed there for 2 or 3 years?
3 years.
3 years. And then since 21, he's back at the university in Liège as a postdoc. His expertise is in the research fields of exoplanets, especially imaging exoplanets, and that's what his talk will be about today also. So, Valentin, you have the floor.
Yeah. Thank you very much, Joris. Hi, everyone. It's a great pleasure for me to give this seminar here and to eventually get the chance to visit this vibrant campus and vibrant city. So today I'll be talking about imaging giant planets that are in the process of forming. So I'll tell you about how we can do this, what were recent discoveries, what we learned from them, and what are the future perspectives in the field. So let me first jump back in time with this diagram showing a classical view of protoplanetary disks as of 10 years ago. So it is a disk of gas and dust surrounding a pre-main sequence star in which a bunch of processes are at work, including grain growth, dust settling, hydrodynamical instabilities, rich chemistry in different parts of the disk, some magnetic fields, you name it, and somehow what happens in there leads to the formation of planets, and more specifically of giant planets within a few million years before all the gas in the disk gets dissipated. And for a long time, all we could see from this disk were just unresolved blobs. And this changed drastically thanks to the advent of ALMA, a 3mm array in Chile, and the advent of new optical and infrared high-contrast imagers at 10-meter class telescopes. And together, they revolutionized our view of protoplanetary disk and of planet formation. So we've now been able to resolve large cavities, substructures including rings and gaps, starting with this impressive image. So I think we were all awestruck back in 2015 when we saw one of these first images obtained with ALMA of the disk of H and tau, seeing all these annular gaps. Now we routinely discover and image these kind of structures in a lot of protoplanetary disks. We've also been able to image spiral arms, both at 3mm wavelengths and in scattered light. And all these structures may suggest dynamical interactions with planets. So we've gathered the pieces of this puzzle of planet formation, and now we need to connect the dots and to directly image those protoplanets that are embedded in this disk and to understand how they are connected to all the structures we are observing, in particular given the fact that indirect methods of exoplanet discovery suggest that exoplanets form around all stars, so in all disks. So let's see what can we expect for the signal of a protoplanet. First, let me step back 1 second. So as you all know, stars form from the gravitational collapse of a molecular cloud fragment. And due to conservation of angular momentum, a disk forms around the protostar. And from there, 2 main paradigms have been proposed for the formation of giant planets in particular. So the first one supposes that the protostellar disk can get sufficiently massive to be gravitationally unstable, and this could lead to the fragmentation of gravitationally unstable clumps, which could then lead to some giant planets. For this to happen, 2 criteria need to be fulfilled. First, we need the so-called Tumri parameter to be small enough. So the Tumri parameter is proportional to the sound speed, so proportional to the temperature and the angular frequency, but inversely proportional to the surface density. So this criterion is typically fulfilled in the outer part of the disk. And but this is not enough. So even if a part of the disk is gravitationally unstable, you still need the cooling timescale to be short enough such that that gravitationally unstable clump can proceed with fragmentation and form a planet. So if these criteria are fulfilled, as I said, it would be preferentially in the outer part of the disk. Now, another paradigm that has been proposed is the one of core accretion, which involves the growth of 13 orders of magnitude in size between sub-micrometer size grains all the way up to fully formed planets. So this involves some grain growth that we know can happen up to centimeter sizes. Then somehow there is a jump of the so-called meter size barrier, which can happen. So one of the main theory now is the so-called streaming instability that can make clumps of dust collapse into planetesimals. Once you have a population of planetesimals, they can hierarchically grow into cores, which can then grow in hydrostatic equilibrium. And if those cores reach a sufficient mass, while there's still enough gas in the disk, they can lead to some runaway accretion of gas and lead to the formation of giant planets as well. So in this whole process, there are only two parts that can be observable. So either the tiny dust grains that can be observed with ALMA or with scattered light, or the population of formed planets. And so far, the statistics of exoplanet discoveries and the properties suggest that core accretion may be able to explain most planets that have been discovered. But this doesn't prevent another formation channel, in particular for giant planets, considering that they must form on much shorter time scale than rocky planets, for example. Now, what about observability? Well, there are different possibilities in terms of how bright we can expect the young planets to be, and this mainly depends on the assumptions made during the accretion process. So if all the energy during accretion is re-radiated, we end up with low entropy for the young planets, so a cold start, or the opposite. If none of this accretion energy is released at the moment of accretion, we can end up with high entropy, so a hot start and a much brighter young planets. But this is not all, because when they are embedded, we expect giant planets to be surrounded by their own tiny accretion disk, a circumplanetary disk. And this has been proposed for a long time already. So just from the observation of the Galilean moons around Jupiter, their properties suggest that they formed within a circumplanetary disk. So the four main moons of Jupiter are on coplanar orbits in the equatorial plane of Jupiter, two of them being in mean-motion resonance. So this suggests that they form within a flat environment, a flat and dissipative environment that allow them to migrate and to lock themselves in resonance. And this is also confirmed with numerical simulations. So when you try to reproduce protoplanetary disks, when you inject a planet in your simulation, you systematically notice the formation of a tiny accretion disk around the planet. So what are the prospects regarding the detectability of those protoplanets? So there have been different approaches. So one of the first approach was to assume that the luminosity would be dominated by accretion luminosity, that is viscous heating dominated. That is basically the friction of the material that's being accreted onto the planet that is creating all the luminosity. So for large enough accretion rates, we can expect this to be larger than the planet, the intrinsic planet luminosity. So we can see here in this plot different expected spectra depending on the accretion rate of the planet and compared to either hot start or cold start predictions. And we can see that in particular at long infrared wavelength, we can expect significant excess compared to the intrinsic luminosity of the planet. So another approach was to follow, to expand basically the models that were made for low mass stars regarding their formation and accretion process, so magnetospheric accretion in particular, and assume that this would dominate the luminosity, so the accretion shock. So either the accretion shock directly onto the surface of the object or the accretion shock on the circumplanetary disk. And in this case, what you'd expect is a significant, potentially significant UV or optical excess, plus a forest of hydrogen lines. So this is for different planet masses, and this is for different mass accretion rates. And in this case, these models basically neglect the thermal infrared excess. So they consider the object in isolation. So another kind of approach is to consider the protoplanet in its disk, in the protoplanetary disk. So you take a full hydrodynamical simulation with potentially some mesh refinement at the location of the planet. You process your hydrodynamical simulations with your radiative transfer code to make some predicted images at different wavelengths. And then you can measure, as you would do in your observations. You do some aperture photometry at the location of the blob, and you can make some predictions that way as well. And the advantage here is that you also take into account the effect of the material around the protoplanet, so the extinction of the dust in the protoplanetary disk. So this has been done by Zuragili and colleagues. And these are a couple of predicted images for different planet masses, and these are the corresponding SCDs for these different planet masses. And we can see that for all cases but the largest mass, at near-infrared wavelength, we expect to be dominated by scattering. So the scattering of stellar light by the dust surrounding the protoplanet. As we see, the slope is consistent with the Rayleigh-Jeans slope of the star. Based on these simulations and predictions, you don't expect significant hydrogen lines to be detectable because there's too much dust around the protoplanet in all cases but the largest mass again. So there's just too much extinction. Now this kind of approach has some limitations as well, because here the predictions are made for a face-on disk for a given planet at a certain separation. So the predictions will change obviously depending on your disk geometry, on the radial separation of your planet. So you have to fine-tune it to the case for which you want to predict it. Okay, so now that we've seen a couple of potential predictions for what we expect for protoplanets, let's have a look at how we can do this in practice. So how can we reach a high contrast and high angular resolution to be able to detect them? So imagine you win at the Euro Millions and you have enough money to build your own 10-meter class telescope in your backyard. Imagine you do this. You may be disappointed by the first images you get, because what you typically see, it's flickering light, some speckles, so quickly varying over time, which are due to the atmospheric turbulences. So the first step is to correct in real time for atmospheric turbulences. So this can be done with an adaptive optics system to reach a higher angular resolution. But that's not enough yet, because even your bright airy rings would still hide any faint flux from a surrounding planet. So you typically need to use a coronagraph to increase the contrast. So a coronagraph is a device that you put in the optical path of your telescope that will block as much light as possible from the star, so from your on-axis light, while preserving as much light as possible from its surroundings. But that's still not enough, because you still have stellar residuals around the star, so you still need a relevant combination of an observing strategy and an image post-processing algorithm to model the residual stellar halo and subtract it to be able to see any planet or disk signal. And there have been different strategies that have been proposed. So the most basic one is to do what we call reference star differential imaging. So you have a target of interest, say Beta Pictoris, with a large circumstellar disk. You observe a similar star to try to have a similar stellar halo and similar speckles, and you use it as a reference and you subtract it, and then you look at the residuals. Now this is time consuming, and you may not end up with the exact same stellar halo. So there have been other strategies that have been proposed as well. So another one is spectral differential imaging, which is something you can do with an integral field spectrograph. So an integral field spectrograph acquires simultaneously images at different wavelengths. And when you have images at different wavelengths, the resolution is proportional to the wavelength. So this means your stellar halo and the speckles will expand with wavelength across your cube, while the position of a planet does not move. So you can leverage that information as well to build a model that you subtract, which is shown here in this square. This is after subtraction, and you can look at the residuals, and you can look at some specific spectral signatures. Sometimes planets are just brighter at some wavelengths than at others. So that's another way to detect them. Another strategy that has been widely used is the so-called polarimetric differential imaging. So this leverages the fact that the light from the star is unpolarized, but after reflection on the dust in the disk, it gets preferentially polarized. So you can leverage again that information to subtract a model of your stellar halo. But the strategy that has been the most widely used so far is the so-called angular differential imaging. And this one basically leverages the fact that when you fix the pupil of your telescope and of your instrument, but then when you track your object during the night, then so you're basically having a quasi-static stellar halo pattern, thanks to the fact that you're fixing the pupil, but the field of view will be rotating. So you can leverage that, and I will show this in the next slide. So you have a relatively quasi-static stellar halo in your sequence of images, while your field of view rotates. So this means any putative planet that is hidden in your field of view would also rotate, and you can leverage that to make a model of your stellar halo. So if you just take, for example, a median of that sequence of images, then the median will mostly capture the stellar halo, but not the planet, and you can subtract it. Then you end up with a stack of residual images, which you then derotate to align the field of view and to align any putative planets, and you finally take a median, or you stack those residual derotated images. Now, there have been a number of algorithms that have been proposed that are more refined than the median, but basically the process is the same. So it's mostly the way that we model the stellar halo that will be different. You can use principal component analysis, for example, or there have been a wide range of different algorithms that have been proposed to better do this. Okay, so at this stage, I'm going to make a commercial break. So have you ever dreamed of imaging a new exoplanet? Have you ever wanted to make beautiful circumstellar disk images? Are you looking to assess the significance of a blob you just detected? Or are you simply looking into evaluating the contrast achieved in your dataset? Well, look no more. Feel like a VIP and get access to a large array of post-processing routines to go from raw images to post-processed images where the stellar halo has been subtracted and where you can look for planets or for protoplanetary disks or disk features in your images. So get access to pre-processing routines as well, so for bad pixel correction, automatic bad frame removal, accurate frame centering, which are all routines that you could apply to your data before doing the PSF modeling and subtraction to improve the performances of those algorithms. You can also have access to diagnostic tools, such as signal-to-noise ratio maps, or what we call STEAM maps, which are somewhat similar. We also implemented forward modeling tools. So imagine you find a planet, you want to know its flux and its accurate position. Then we can use what we call for negative fake companion technique to estimate the accurate flux and position of the companion. We also implemented contrast curves, which allow you to estimate the achieved contrast as a function of radon separation. So this tells you how faint planets you would have expected to see, even if you haven't found any planets in your data. So VIP is instrument agnostic. It is well documented. It is also beginner friendly. We made a lot of Jupyter notebooks, Jupyter notebook tutorials to get used to different routines. So we have both procedural and object-oriented implementations in VIP. And so we're welcoming any contributions, and we also have a set of automated unit tests so that we don't break the code at each new contribution. So what are you waiting for? Find your own planet now. Terms and conditions apply. Okay, so after this commercial break, let's go to the discoveries that have been made, mostly thanks to angular differential imaging. So there have been about 20 or so giant planets that have been imaged to date. And here is a gallery of the most significant discoveries. So this is the very first planetary mass companion that has been imaged. So it was back in 2004 with the NACO instruments. This was a planet around a brown dwarf. So this is the famous Beta Pictoris system. So it's a planet that had been predicted for a while because there's a large circumstellar disk that we don't see in this image, but which presents some wiggles, which suggested the presence of an embedded planet. So this was, it was found in 2003 on one side of the star, and then a few years later it had moved to the other side. And probably one of the most famous one is the HRT 799 system with its 4 different giant planets. So it's like a scaled up version of our own solar system. This is an A-type star with 4 giant planets that are larger than our own giant planets. And this week, there's been a new addition to this gallery. So it's a new giant planet, the lowest mass giant planet with an accurate estimate thanks to astrometry as well. So it's AF LEP-B. It just came out on arXiv a few days ago. What's the point in common between all those discoveries is that they were all made thanks to 10-meter class telescopes. So the VLT or Gemini or Subaru or Keck observatories. So there have been lots of large surveys for direct imaging. So these 20 or so detections correspond to a very small detection rate. So the occurrence rate is about 1% for planets of 5 to 10 Jupiter masses between 30 and 300 AU. So this is relatively low. Now what's interesting as well is that most of these discoveries suggest, most of these discoveries, at least the ones where we could get some separate dynamical constraints, such as HRT 799 or Beta Peak, where we have, in this case, a disk, or here several planets. So we have some dynamical constraints for the stability of the system. So we have a separate estimate of the mass. So both the mass and the luminosity suggest that these are mostly consistent with hot start models. What's also interesting is that separately, ALMA has probed very large protoplanetary disk with substructures extending up to 700 AUs. So one question is whether what we're seeing here are simply evolved very large protoplanetary disks, which could also be outliers. So these disks have been a priority for observations with ALMA because they're the brightest and the largest, so the easiest one to observe. Now to set better constraints on planet formation, we need to look at even younger ages. So what about protoplanets? So there have been a number of protoplanet candidates that have been proposed for the past 10 years or so, on average with one new candidate every year. A lot of them are not very convincing, to be fair. I think the community agrees that the only system so far with confirmed protoplanets is PDS-70, which has detections both at infrared wavelength in the H-alpha line and at sub-millimeter wavelength. So let me go a bit deeper into that system to start with. So this system has a very large cavity, so about a 50 AU cavity, so it was a prime target to look for an embedded planet. And it was found with different instruments at the VLT, including Sphere, Symphony, NACO. So we found this point-like source here in the cavity. Then soon after, a second protoplanet was claimed thanks to the VLT Muse integraphy and spectrograph, and probing more specifically the H-alpha line. So the H-alpha line is a tracer of accretion. So it's something you expect from accreting planets, since it's tracing hot gas, basically, in falling onto the planet. So these images show not only a point source at the location of PS70b, but an additional point source in the disk, which retrospectively also matched a knot or a blob in the infrared observations. But since that blob was very close from the edge of the cavity, it was not claimed as such back then. So I said this suggested ongoing accretion from the two protoplanets. The detection at different wavelengths allowed us to carry out some spectral characterization. So we compared the spectrum we could extract, both from photometric points at different wavelengths and low resolution spectra. And we compared this to a range of atmospheric models. And we noticed that this could not be explained by just an atmosphere, that the spectrum was more consistent with some infrared excess. And this, together with the fact that ALMA images suggested the presence of two compact signals in the cavity at those two locations, suggested the presence of circumplanetary disks surrounding each of the two giant planets. So we also carried out hydrodynamical simulations to try to reproduce all the observed features of this disk. So so here are the predicted images that are output from that are obtained after processing, relative transfer processing of the hydrodynamical simulations, and this is compared to the observations. So we see that we have a fair fair qualitative match of the different structures, and this is even more so when you consider that the only thing we did for the hydrodynamical simulations was to inject two planet seeds in the outer part of the disk and let them free to accrete material and to migrate. And they migrated inwards until they locked themselves in resonance, close to the 2-to-1 resonance, which is also what we observe for the PS70b and C planets, which appear to be in 2-to-1 resonance. So we could, thanks to these hydrodynamical simulations, explain the architecture of the system, the wide cavity, and the location of the two planets. We could explain it as a natural outcome of migration and resonance locking of the protoplanets. So since then, there's been additional follow-up studies on this source. So PS70b was also detected by a new reduction of archival Hubble Space Telescope data. So this gave two more points, one at optical wavelength, another one in the H-alpha line. There was a new, better quality spectrum obtained at K-band thanks to gravity. So this led to new spectral characterization studies, which reached similar conclusions as before. So we see that the best fit model is actually one that corresponds to an atmosphere, but with a little bit of extinction and with some extra components, some infrared excess that we represent with an extra black body contribution. And plus some accretion shock signals to reproduce the hydrogen lines and the excess continuum at optical wavelength. So gravity also enabled precise orbital characterization, so a determination of the orbital elements for the two protoplanets. And this suggested that both of them are close to circular orbits, so the eccentricity is negligible for both of them. Now, this is not the end of the story. So we, so based on this best fit model here, we expected a redetection using a different technique that's called cross-correlation with templates that correspond to these best fit atmospheric models or to molecules that are included in those models. But surprisingly, we did not. So if we try to cross-correlate these templates corresponding to different molecules to integral field spectrograph data, you would expect a peak, some signal, some peak in cross-correlation at the location of the protoplanet, which is not observed. And so when injecting fake planets with these best fit models that match at low resolution, we would have expected to see that signal. So this is a bit puzzling. So it suggests either that there is much higher extinction than originally expected, or that despite good and low resolution fit, the model does not really is not really appropriate, the atmospheric models that we use. Now the latest submillimeter image of the system unambiguously confirm a circumplanetary disk around protoplanet C. Now when the reduction is done with slightly different parameters, so to not go into the details, you can when you reconstruct your ALMA image, you can play with one parameter to either increase the sensitivity at the cost of angular resolution, and if you choose that parameter accordingly, you can see some extended emission around protoplanet B. But if you change that parameter to increase the angular resolution at the cost of sensitivity, then you see much better the material that we interpret, the signal that we interpret as cold dust in the circumplanetary disk around the protoplanet. And this is not yet over. These are data obtained with the James Webb Space Telescope, and more specifically with the MRS, so the mid-resolution spectrograph of MIRI. So we obtained two interesting discoveries. We got two interesting new discoveries with this. First, we noticed that there was a significant variability between the spectrum that was obtained with Spitzer, which is shown here, and which also match a couple of photometric points, and the new spectrum we obtained with MIRI. So that the difference is quite significant. We cannot explain it just with some potential calibration issue. Plus, we also have photometric points obtained independently that either match one or the other spectra. So this suggests that there is true variability, which could be due to a warp in the inner disk of that system. What we also see in this exquisite quality spectrum, we can zoom in different regions of that new spectrum. And in particular, in the 7 micrometer region, if we zoom in, we can try to fit the forest of lines that we now see with MIRI, with the spectrograph. And it is well fit with a slab model of warm water. And the best fit is obtained with a temperature of about 500 Kelvin. And this would be for water that's very close in from the star. So this is also something we were not expecting. Another interesting discovery. Now, to be fair, there has been another claim of protoplanets after PDS 70, which is AB or B. So I won't go into the details of explaining that discovery. I would say it is still debated. Over the author's claim, it is confirmed. the community is still a bit balanced, and there's not as much evidence yet for that one than for the PS70 protoplanet. But what I can tell you is our new discovery. So this is a discovery that was led by my PhD student, Ian Hammond. So we observed this protoplanetary disk, this transition disk. So transition disk is a protoplanetary disk with a large cavity. So in this case, we see there's a bright inner ring and a second ring and a large annular gap in between. So if we look at these different images obtained with the sphere high contrast imager, we see that there is some compact signal here. So just considering that single image, it's not very convincing. But then we followed up the source over time, and in different epochs, we see that compact signal that is moving over time. On top of that, we also see an outer spiral wake, so in the vicinity of the protoplanet, which is also what you expect from hydrodynamical simulation. So from a planet in a disk, you expect it to create a spiral wake. So if we collect all the pieces of evidence, so we have the detection in 4 different epochs of data. If we plot the astrometry over time, and in particular the position angle, and if we compare it to the prediction for a Keplerian orbit at 37 AU, we see that it is consistent with a Keplerian orbit at the radial separation of the signal. We tried to get some constraints on the spectrum, but the object is so faint that we had to bin spectral channels together. So there are 39 spectral channels in the IFS of sphere, but you had to bin them in three bins to be able to still have some signal to measure at that location. And we see that the contrast with respect to the star is relatively flat as a function of wavelength. So this is in tension with, for example, the spectrum of PDS70b that is shown here after rescaling, but it appears to be relatively consistent with what you'd expect from a circumplanetary disk. If you remember the slide I showed earlier, in this wavelength range, if you have a lot of dust, you may be scattering dominated. In that case, you expect a flat contrast with wavelength. So another piece of evidence is that we have the spiral wake, which you'd expect from hydrodynamical simulations. So this is not a model that we have optimized for the system. Actually, it was a model that was published before the discovery. So we just compare it, but we know that, for example, if we change the flaring of the disk, we can have a different aspect for the annular gap. Our point is that qualitatively we can reproduce both the annular gap and the spiral arm. And another interesting fact is that when we look at previous publications of this source, in particular a publication by Madalena, who is just here, and Madalena and the Liège team, in 2014, in old NACO AGPM, so AGPM is the chronograph we developed in Liège. In those observations, if you mask the inner part where you have a bright inner disk, then you see that there's actually a spiral wake and a faint signal there. So of course there's a lot of noise, but at least we see something where we expect it. And this is at a different wavelength. This is at M prime band, so at thermal infrared wavelengths. So altogether, we have collected quite a few pieces of evidence, I guess, to have the ultimate confirmation that this is indeed a protoplanet. We need observation with this guy that you may have heard of, and in particular chronographic observations with MIRI at 10 micrometer. So with I think it was 6 hours integration time, we can achieve this sensitivity with MIRI at 10 micrometer. And here we've compared different models of circumplanetary disk with respect to our measurements at near-infrared wavelength. The upper limit obtained with ALMA, since there is no signal at 2 millimeter wavelength at that location. and there is no signal either at K bands with sphere. So we compare our measurements with different CPD models, and we see that for most models, we expect them to be above the sensitivity of MIRI at 10 micrometer. So the measurements that we hope to be able to make, if our proposal gets accepted, could constrain the nature of that object and confirm that it is a protoplanet surrounded by a circumplanetary disk. So these are the most sensitive ALMA observations of that system. So as we can see, there is no signal there. This was at 1.3 millimeter. So in another study by Zulagi and colleague, they suggest to rather use the band 9, so at 0.4 millimeter, and with reasonable integration time with ALMA, we can expect to achieve this kind of sensitivity. So we could also put some constraints on the possible circumplanetary disk models. Okay, so apart from PDS-70 BNC, HG169142B, there have been, as I said, a number of candidates where it is much less clear. For example, in HG100-546, there have been 2 protoplanet candidates that have been claimed in Lycasium-15 that you may have heard of as well. So this was a Nature publication where they suggest that there could be 3 protoplanets. So there was another study that we led, and where we found a very faint point source next to an M-type star, and this point source is 7 magnitude fainter than the star, so a priori it could be consistent with a protoplanet in terms of absolute magnitudes. But it turned out in this case that the spectrum that we inferred from it was more consistent with an M dwarf, so a very obscured M dwarf, that is hundreds of times fainter than expected, which we could explain with, for example, an edge-on disk that is blocking most of the light from that source. But in these cases, the most significant problem is that the techniques, the algorithm, the image processing algorithms that were used to reduce the data are very aggressive, and they can filter extended signals from the disk into point-like sources, and this can lead to false positives. And there's a good chance that a number of the protoplanet candidates that have been proposed in literature just correspond to filtered extended disk signals. And so to clarify the status of these protoplanet candidates, we've been developing new image processing algorithms to be able to answer that question of whether they are indeed protoplanets or not. And to illustrate the effect of filtering, I'm just showing here the effect of these algorithms on a model, on a toy model disk that represents PDS-70 with a large cavity and scattered light signal from the edge of the cavity. If you process this with either median ADI or with PCA that I mentioned earlier, you can end up with very different intensity distributions due to the filtering by the algorithm. So you can create an artificial bulge, some self-subtraction in areas where the signal is azimutally constant. You can even end up with spurious multiple arcs, and when you compare that to images published in the literature, you can see these same artifacts in the published images of the observation of PDS-70. Fortunately, in this case, it doesn't jeopardize the authenticity of the protoplanets. But this can lead to a number of false positives as well for the disks. So what can we do? So we've implemented a new algorithm that's called FEV, for fractionation of embedded very young exoplanets. And the idea is to use an iterative process to estimate at each stage what is significant in your image, and to remove it from the model you're subtracting of your stellar halo. And you do that iteratively, and you do it in different areas of your field of view, in smaller and smaller areas. So how does it look like in practice? So the very first image you saw was what you obtained just with PCA. And this is as you increase the number of iterations, and when you remove the signal from the disk, from the model you're subtracting of the stellar halo. So you're less and less biased by self-subtraction. And you can see you recover better and better the extended spiral structure for this protoplanetary disk. So this is one approach. Just to show the difference, this is the very first iteration, so when there is no iteration, just a simple PCA application, and this is as you increase the number of iterations, then you progressively recover this signal. Another approach that we've been investigating with my PhD student Sandrine Juillard is to follow an inverse problem approach for this. So we're basically modeling, in this case, all the images of the sequence, of the ADI sequence, and we say that there is a static contribution, that is the stellar halo, that doesn't change much, and there is the disk contribution, disk or planet contribution, which is rotating in your different images, and there is some errors or misfits. So we're trying to minimize these errors to recover both S and D, and in particular the D components, so the disk and the planet. And this is how it looks like in practice. So this is your cube of images, where your field of view is rotating over time. This is the estimation for the static contribution. This is the estimation for the rotating contribution. And this is the noise that you're trying to minimize. And with this, if we apply it to the model I just showed earlier, we see that we can get a much more unbiased final image. So we recover an intensity distribution that is much closer to the input in this case. So this is much more promising to try to clarify the status of protoplanet candidates. Now we're in the process of applying these new techniques to archival data to clarify the status of protoplanet candidates. So now talking briefly about future perspectives. So apart from direct imaging, there are different approaches to try to confirm and characterize any protoplanet. And another one is using, a very promising one, is using ALMA, in particular channel maps with ALMA. So ALMA not only has a high angular resolution, but also a high velocity resolution. So you can leverage the high velocity resolution to probe different parts of the disk. So due to the Doppler effect, the gas in the disk has different radial velocities, and if you probe it at high enough velocity resolution, you see this typical butterfly pattern, which you can predict or model pretty accurately, knowing the geometry of the disk. Then you can look for any deviation from this butterfly pattern. And this is what was done here. And in the past few years, there have been a couple of so-called kinks, so deviations from Keplerian kinematics found in those channel maps. And this is shown here. This was the first kinematic detection of a protoplanet. It was suggested by Pint and colleagues. So we can see here, instead of having a smooth butterfly wing, we have this this kink, which we can also see for this data set here. And what was interesting for this one is that the location of the kink corresponded to an annular gap, which provided some additional confidence that this was tracing a protoplanet. Now there is some expected synergy with James Webb. So James Webb has a very high sensitivity towards planets and protoplanets at mid-infrared wavelengths. And if we combine this with ALMA, we can expect to have both an estimate of the luminosity, independent estimates of the luminosity and the mass of the protoplanets, which could bring the most stringent constraints on planet formation models. So these are a couple of simulations we did for the disk I just showed earlier, where we observed the kink of how a protoplanet would look like at mid-infrared wavelength with James Webb, assuming different masses for the protoplanet. So we see that we can expect to be sensitive down to 0.5 Jupiter masses. So another instrument that could be particularly relevant for us is IRIS. So it's a new infrared imager and spectrograph at the VLT, which is basically replacing NACO and Symphony. So it has a new detector, refurbished integrated field spectrograph, an improved adaptive optics system, including laser guide star, which can allow us to probe even fainter objects and hopefully help us confirm any new protoplanets. But what could be a game changer is METIS, the mid-infrared imager and spectrograph of the extremely large telescope, which we expect to be sensitive to much fainter planets and potentially to nearby super Earths, thanks to both its high sensitivity and high angular resolution. So just to give you an idea of the improvement we expect with DLT and METIS, this is what we have with current 10-meter class telescope, the kind of images we have for a protoplanetary disk, and this is what we expect to see with METIS. So much finer details in the spiral structure, which could allow us to pinpoint the location of planets. So in this case, there's still a lot of degeneracy regarding the location of planets that could trigger this spiral structure, which we hope to break with much finer details imaged. And with METIS, we expect to be able to carry out this similar observations as with ALMA, but probing warm gas instead of cold gas, so probing row vibrational lines instead of rotational lines, but essentially the same, so to pinpoint the kinematic signature of embedded planets and their circumplanetary disk, so in different channels. And hopefully this could help us get a population of protoplanets and have some more discoveries to compare the PS70 B and C protoplanets to. Oops. So let's summarize what I presented. So as I showed you, new instruments and techniques in the past few years have completely revolutionized our field, our view of planet formation, in particular the PS70 B and C discovery and follow-up has provided us a lot of information about the process of planet formation. In particular, it confirmed what we expected regarding the presence of circumplanetary disk around forming giant planets. We could explain the configuration of protoplanets B and C with hydrodynamical simulations which reproduce migration and resonance locking. There's still some uncertainty regarding the spectrum, because at low spectral resolution, it appears to be compatible with mostly an atmosphere with some circumplanetary dust, but this is not confirmed at higher spectral resolution. So there's still, so this discovery actually triggered more questions. In particular, is this system really an outlier, or is it representing most forming giant planets? How would protoplanets look like at younger ages? And I presented a new, very promising protoplanet candidate that we expect to confirm with James Webb. And we already have gathered a number of pieces of evidence to show that HD 169142b is a strong candidate. For other candidates, it's much less clear. So we've been developing new image processing algorithms to clarify the status of those candidates. And what's really on top of the wish list of a lot of us working on planet formation is to have independent mass and luminosity estimates for those protoplanets to really have the most stringent constraints on planet formation models. So stay tuned for upcoming results on transition disk in which we may find more protoplanets. So thank you for attention, and I'll take any question.
Thank you, Valentin. Very interesting talk, fascinating topic. Are there any questions or comments or feedback?
Yeah, thank you for this very interesting presentation. At the very beginning, you mentioned the difference between hot start and cold start, mentioning it's whether the protoplanet has a chance to radiate the energy, and but that is, if I understand correctly, this is only a matter of how fast it gathers this energy, that it forms, right? Or am I missing something? Or is there another process that could prevent it from shedding its energy radiatively?
So I'm not really an expert on this, but I will assume it depends on how the material is coming onto the planet itself that could change the amount of energy that is released at the moment of accretion. But yeah, it's interesting to note that there's been a change over time. Let me go back to that specific slide. That is historically cold and hot start models. So hot starts were first associated to gravitational instability and cold start to core accretion, but this view has changed, and that now we think it's just the accretion process and the uncertainty of what's really happening during the accretion process that is driving either one or the other prediction, or a range somewhere in the middle, what we call warm starts.
Okay, but there's still uncertainty on whether each would go towards hotter or colder start.
Yeah, it's unclear. So different studies point to different directions. So there have been this recent Berardo et al. Paper, which suggested that even core accretion could lead to hot starts as well. So it's a bit unclear.
Thank you.
Any more questions?
Yeah, very, very nice talk, Valentin. I was just wondering for PDS 70B, what is, approximately K-band magnitude, and also is there any kind of extent? I mean, is it a point source, or is there any kind of indication of being a more extended source, maybe with these. What did you call it, circumplanetary disk? I mean, that could give some hints to that.
Yeah, so at infrared wavelengths, it is definitely point-like. At submillimeter wavelength, as I showed, actually it's in the next slide, it depends a bit on how you reduce your ALMA data. So with this robust parameter, if you tune it to be more sensitive, to faint signals, but at the cost of angular resolution, then you can see what looks like some almost resolved emission around the protoplanet. So there could be some diffuse emission from dust around the protoplanet, which could be affecting also the spectrum at infrared wavelengths. So this could explain why we need to include some extinction to be able to reproduce the infrared spectrum, and some minor infrared excess as well. But yeah, at infrared wavelengths, we just see a point source.
Hey Valentin, for this new planet discovered on AF Lab, do you know if there is an ALMA image, and if the outer disk is carved by this planet?
No, I haven't had the time to look into it. I don't think there is ALMA image, or at least it's not published. But yeah, what's interesting is that 3 different teams publish at the same time. So there was a bit of drama in the community because some said that one team tried to scoop the other 2 ones. Let me get back to that image. The one I showed here was actually obtained at L prime bands, so this was with Keck. But the other, so this is from the Franson et al. Paper, and the other 2 focused on sphere detection, so it was at near infrared wavelengths. and this is at thermo-infrared wavelengths. So I don't know much about this source in particular, so it just came out this week, so I haven't had the time to dive into it. But I noticed that there were a lot of archival NECO data on that source as well, and that was not published, so maybe worth investigating a bit further as well.
Thank you for the very nice talk, and also thank you for the efforts that you put in VIP, because that's a very useful software, not only for planets, but we've been using it a lot here too.
Now that you mentioned it, this was obtained with VIP, so I was very proud when I saw in that publication they used VIP.
Very nice.
To obtain these images.
I have 2 questions. The first one is, I mean, one of the efforts for future work, right, is to find more of those planetary systems with circumplanetary disks. Sorry, what will you learn from more objects? Because you already seems to know that those planets have formed in the gaps in the disks.
So with PDS-70 B and C, we just have one snapshot at one particular moment in time, and we think it's relatively late in the process of planet formation. So the fact that we don't see that much extinction in the end, the fact that the estimated accretion rates onto the planets is quite small, suggests that they are nearing the end of the formation process. So what would be interesting is to know what happens earlier, and my guess is that what we're seeing with HG 169142 is that we're probing it at an earlier stages when it is much more enshrouded in dust. And this is something I'd like to confirm, that there is this process with a maybe thick circumplanetary disk or envelope around the protoplanet that gets accreted over time. So yeah, we'd like to have a range of different timestamps to better understand the process of planet formation. And compare the properties. So if we have a statistical sample, then we can start to say whether it's a common formation channel for all protoplanets, or whether there could be different formation channels as well.
All right, thank you for that. The other question is of purely technical nature. There's an entire set of other algorithms for image processing that you did not mention, which is artificial intelligence and machine learning.
Yeah.
Do you have a comment on those?
Yeah, that's also a very promising approach. So far, it's difficult for the case of disk, of extended signals. So it's something that's also investigated in Liège in the group of Olivier. But so far, it's mostly to detect point sources. Because it just gets way too complicated when you have extended signals. So, but maybe at some points we could try to use that as well to try to pinpoint protoplanets, embedded protoplanets.
Thanks, Valentin, for the talk. I have a question regarding HG 169142, because so the reason why initially we started direct imaging that object is because there were some millimeter observations that showed that there was some emission coming from the gap, but when we look at that in the L-band, we couldn't find any protoplanet there. Have you tried to overlap these VLA observations with the new data?
We haven't yet, but that's a good point. I'd
I
forgotten
don't
about that
think it's
publication.
where
but yeah.
we expected the protoplanet to be, but I think it would still be nice to see if there's a...
I think it was at a different location, if I remember correctly. It was much more south.
Yeah.
So it probably doesn't match our discovery.
But since, I remember that this millimeter observation would somehow, kind of composed of several different blobs. I think it would be nice just to see if we can understand better this millimeter emission given the new set of observations.
I think they were also obtained at relatively low angular resolution, so it was maybe difficult to interpret as well. In the meantime, there have been those images published by Seba Perez and colleagues, which is the one I showed in the presentation. Here. So this is probably the most sensitive ALMA image obtained in the submillimeter continuum. And we don't see much there, but this may still be consistent with our scenario, because for some predictions where you expect to be orders of magnitude fainter than the limits that were set there. So that's why some colleagues suggested to observe at shorter wavelengths, so in the band 9 continuum, where we have a better chance to capture that. So I'm not sure, whether we could expect to see any emission even at longer wavelengths as well. Mm.
Anyone else? If not, then let's thank Valentin again. Thank you very much.
No worries.